Going anywhere with it. All right, so we're going to talk about polynomial functions for the next little while in chapter 5. But polynomial functions are a lot like quadratics, they're just bigger. A lot of the same things happen with those. And what we've got there at the top, the f of x is equal to a sub n times x to the nth power minus a sub n minus 1 times x to the n minus 1 power. That's like the generic version of that. Those a sub n's that are in the front, they're just real numbers. Okay, they're not, not variables. They're just numbers. And this the subscript is just saying, okay, this is the term or the coefficient in front of that power, that sort of thing. And then the n for both the exponents and the subscript are non-negative integers. Integers. What's an integer? What kind of number? Okay, but positive and negative whole numbers, or non-negative integers would be just the positive side. So we're talking about whole numbers for that. And then to be a polynomial function, there are some rules that you have to follow. One of those rules, now the dot, dot, dot in between here is because, if you start with n to the fifth, x to the 5th power, you'd have more of them in between than if you started with x to the 3rd power. So like, depending on how big the degree is, we'll talk about that in just a second, can determine how many terms you'll have there. So to be a polynomial, so maybe I need to label that, to be a polynomial function, the rules are that you have no negative or non-integer exponents. No negative exponents, no fraction exponents. So like not an x to the 2/3 power, not a square root of x, because the square root of x is 1/2 power. Not a cubed root of x, because that's the 1/3 power. So it has to be positive integer exponents on our variables there to be a polynomial function. Also, no rational expressions. What's a rational expression? Anybody know what a rational expression is? Well, this word should give it away. Yeah, denominator, that's got to be a fraction. It's got a denominator, it's a fraction. Example of that, f of x is equal to x squared plus 5x minus 7 over x plus 4. Not a polynomial. So no variables in the denominator. Variables in the denominator really are created by negative exponents, so that's the reason they don't exist there. What's wrong with it? All right, so those rules, follow those. You got a polynomial function. No negative exponents, no non-integer exponents, so no fraction exponents, and then no variables in the denominator is basically what you got to remember. And so that takes away one of the red flags when we talk about domain. Okay, so when we talk about some of the properties of a polynomial, what was that? Not a polynomial. That function right there is not a polynomial because it has the x plus 4 in the denominator. That's an example of one of those that's not a polynomial. All right. Domain of a polynomial is negative infinity, positive infinity. What's that just like? Quadratics. Quadratics have the same domain from negative infinity to positive infinity. They don't have any red flags. They don't have square roots in them because you can't have a fraction exponent. They can't have variables in the denominator. So that's the only two red flags that could exist to change your domain. They don't have those. So the domain has to be all real numbers or negative infinity to positive infinity. Out of that. The range, however, will change depending on what degree of the polynomial and all that stuff we have. So let's define what degree is. Maybe you remember this from Algebra 1. We just talked about this in Algebra 1, so I think of that. Degree of the polynomial. You may remember what that is. Linear equations have a degree of 1. Quadratic equations have a degree of 2. So cubic have a degree of 3. Quartic have a degree of 4. So where is that degree coming from? The highest power. That's exactly all it is. Changes with every problem. It's the highest power or the highest exponent on the variable. And in our case, that variable is x. All right. So we're going to play the game. Is this a function? And then the bonus points are for what's the degree. So is the function a polynomial? If so, state the degree. All right, example A. F of x, so it's a function, we know that. 3x to the fourth power minus 5x to the third. It's 2x squared plus 6x minus 7. Is that a polynomial? All right, so it satisfies what rules? That are what? Non-integer. Okay, so all the exponents on the variables are integers, 4, 3, 2, 1, 0. Those are nice integers. There's no variables in the denominator. So it satisfies those two rules. So it is a polynomial, and the degree is 4. Easiest thing you've done all year. Well, you're going to need to know that. You know, we're obviously going to do more than that, but you're going to need to recognize the degree is a really important thing, especially when we go to start solving these. If you don't know the degree, you're going to struggle with finding, knowing how many answers you should even have, because the degree changes that. And also, what tools that you can use to solve based on the degree. What's the problem? No fraction, and the reason is fraction exponent. That's why. So we don't have it. It's not a polynomial, so we don't even state the degree of it. It's not a polynomial, it doesn't have a degree. One half is a fraction. That's against the rules. No.
Yeah. It looked like y squared.
G of x is y. There's no way there's another y. It's a 1/2. What about C? Why not? It's a fraction exponent. Remember from Algebra 2, x to the 1/3 is what the cube root is. So that's not a polynomial. All right. Get a little room here for example. H of x is equal to 2x cubed, parentheses, x plus 4 squared. Okay, no fraction exponents, no variables in the denominator, so we're good. We follow those rules. So it is a polynomial. No. If you multiplied it out, what is the highest degree? So this multiplies out, you're going to have an x squared, right? And then you're going to multiply it by an x cubed. So x squared times x cubed is going to be x to the 5th power. So the degree is 5. Let's do another one of those just to make sure we understand that. So let's say we had 1/5 x to the 8th parentheses x squared minus 4 to the 3rd. Is that a polynomial? What about that 1/5? Why is it okay? It's not an exponent. That's right. So that 1/5 is okay. It's not an exponent. So yes, and the degree how? Explain why. That's not cubed. So you're cubing this. So x squared times x squared times x squared is x to the 6th times x to the 8th will be x to the 14th, so degree of 14. And what that's going to equate to later on when we start solving these is that whatever the degree is, that's how many answers you should have. Yeah, we won't get to any. We won't solve any that have 14. We'll, we don't get too large with that because it. Yeah, no. 5th power is probably about as big as we get, so we don't get too crazy with that. All right. Now, there is a table on page 328. There's a number on that table. There are several tables in this chapter that I want you to pay attention to. So page 328 in the textbook. There is a table. It's table number 1 for this chapter. And we're gonna take the idea of that table and kind of extend it, maybe get a little better understanding what some different polynomials do. All right, so we're gonna make that chart: degree, form, name, and kind of what the graph looks like. So I'm gonna make a table here. All right, so f of x equals 0. It has no degree. It's kind of weird. Okay, doesn't have a degree. There's no degree when y equals 0. The name of that is very simple: the 0 function. If I were to graph that, what's it look like? It's a coordinate plane, and it's a y equals a number, happens to be y equals 0, so it's a horizontal line just right on the x-axis. It's right on top of the x-axis. That's what the graph's going to look. So we're just going to draw a small sketch over here with the graph and maybe describe it a little bit, which they don't do in that table. So I'm trying to give you a little bit more than what they're giving you. Okay. So the next thing, if it has no degree, the next degree that we could deal with would be 0 degree. There's a difference. No degree happens when y equals 0 or f of x equals 0. Degree of 0 is when we have y equal to some other number. And since we're in the polynomial section, the way they denote that is a sub 0. Okay. And that's the constant function, which you learned from the library of functions in chapter 3. A constant function. So graph, it's still y equals a number. It's a horizontal line, right? But it's not on the x-axis. It's anywhere else. So it would be wherever, a sub 0. Horizontal line at y equals a sub 0. Whatever a sub 0 is. whatever number it is. When we get to some real problems, we'll have numbers in there. Can't do anything real yet. All right, so let's build up the degree of 1. And that would be a sub 1 times x plus a sub 0. That's the polynomial way of writing it. We did this as mx plus b in chapter 3 and chapter 4. So that was what kind of equation? Linear. Okay, so it's a linear. To 0. A sub 0. Subscript 0 is what that means. It just the reason they're doing that is because the degree is 0. When you look at this one, the degree is 1, and that's a sub 1. The coefficient in front of the part that tells you the degree is got the same subscript as the degree is. That's why they were trying to tie that together. That's why they use that way of naming it. So a linear function, coordinate plane, could have a positive slope, could have a negative slope. We'll be optimistic today and give it a positive slope. So think y equals mx plus b. Think about it. That's what it is. That's what a linear function with it's a polynomial with degree of 1 is what that is. So when you get to degree 2, this is stuff we've already done. The quadratics. So a sub 2 x squared. A sub 1 x plus a sub 0. Quadratic. What we called that. And we know that the graph of that looks like what? It's a parabola. So it could open up or it could open down. We're going to be optimistic and have it open up. So all of these things we've already done. We should know how to solve those, how to get parts of the graph for those. All of those things up to this point we've already done. So let's get to the stuff we hadn't done. Higher degree. But you actually have done this in Algebra 2. If it's got degree 3, then the highest exponent is cubed. So a sub 3, x to the third, a sub 2, x squared, a sub 1, x, a sub 0. And that's called cubic. The graph of a cubic does something like that. And depending on what numbers are in front of each x to whatever power, changes how much or how tall or skinny and all that stuff. All those coefficients are going to change that. But the general shape of a cubic is that. So up, back down. Should know the general shape for x cubed anyway from chapter 3 in the library of functions. But by adding all these extra things here, it's going to change how tall the hump and the trough are on that. Okay. And then we'll go to fourth power. I don't know why I'm writing in blue there. Don't mean to. Fourth power f of x, a sub 4, x to the fourth power, and so on. Plus a sub 0. That's the last one we're going to write down. We could continue this forever if we want to do, but I mean, it starts repeating itself after this. Okay, so we get to the fourth power. You can call it quartic, Q-U-A-R-T-I-C, or most of the time you're going to hear me call it a fourth degree polynomial. That's what I've always called it. Most mathematicians don't call them quartics unless they're just showing off. That is possible that you go to a calculus class and they call them that, but I doubt it. Fourth degree polynomial. Degrees 4. I might not even call a cubic. I might say it's third degree polynomial. To me, that's more descriptive and maybe helps you a little bit more understand what we're dealing with. So the graph of that can vary quite a bit. It could look exactly like a parabola, but because it's fourth degree, it can change a little bit, and it could have like various, up to looking like kind of like a W, but with round curves instead of maybe a cursive button. But because it's fourth degree, and the coefficients in front of all of these other pieces, the x cubed, x squared, x, and then the constant will change how much, variation you got in that little W's area of that. But notice, here's what's happening. Fourth degree, the end behavior, look at the ends, they're both going the same direction. Squared, quadratic, no matter if it opens up or down, they're both going in the same direction. Odd degree here with the 3. One end's down, one end's up. When you look at the linear piece, its degree is 1. It's odd, right? One end's pointing down, one end's pointing up. That's the consistency that we're after here, is that if it's got odd degree, the end behavior, one end's going to go down, one's going to go up. Depending on the numbers that are in there, which end does what. And then on the even degrees, squared, fourth power, sixth power, 8, you could go any even ones. They're going to look something like this. We know both ends are going to go the same direction. So that's something we need to recognize and know with that. So kind of start filing a few facts away here to this and thinking about that. So let's look at just some graphs and a few things here for this stuff, and then we'll get into actually doing a little bit of algebra today. So we're going to graph, and when I say graph, I want you to use your graphic calculator out of this and try to be able to adjust and visualize things with it. So I don't know what letter F is what letter we're on. So we're going to graph this function. F of x is equal to 1/2 x minus 1 to the fourth power. Before we type that into our calculator, I want to talk about it. What do we know about this polynomial? What's its degree? 4. So it's an even degree. So we know both ends should do what? Go up or down?
Either one.
Well, it's going to be one or the other. Why up? Positive leading coefficients. The same way the A on a parabola, on a quadratic, if A was positive, it pointed up. If A was negative, it went down. With a fourth degree, the same rule. Whatever's in front, if it's positive, it goes up. If it's negative, it goes down. So that rule doesn't change there. So we already know a lot of things about this graph just because we know the degree and we know the number that's going to be in the front if you multiplied it out. Those are good things to know that speeds you up on everything else. All right, so let's look at the graph of that. Make sure if you got stat plots turned on, turn those off. If you've got one of your plots up here highlighted, just arrow up there and hit enter and it'll turn it off because it'll mess up your graph if you got that on there. So I turned all mine off the other day. So 1/2, you could type in 0.5, it doesn't matter. X minus 1 raised to the fourth power. And I'm going to hit graph. Now that looks a lot like a parabola, doesn't it? But it's not exactly like a parabola. It's a little, looks like it's not quite as pointed as a parabola is down at the bottom. It's a little wider. That fourth power makes it a little broader at the base. It flattens out kind of down here at the bottom out of that. So we see that's been shifted. Kind of looks like what would be the vertex of a quadratic is right there, right? So if you look at the polynomial and think about transformation wise, what does the x minus 1 in parentheses do? Right 1. So look at the bottom of that graph. It's this shape that is moved over a little bit here. So that's remembering our transformations back from we did that chapter 3. So some stuff there that's going to happen. So there's our graph. I'm going to take a snapshot of that and put it in our notes. You just need to remember, hey, that's what that looks like. Remember the things we talk about. I have no idea why it distorts it when I copy and paste it, but it does. That's a pretty good looking graph. F G, f of x. And guys, this is should be a squared there. Sorry, my 3's in the next problem. Sorry. The thing that I'm after here is to recognize before we even graph it that we can visualize what it's going to look like because we know the degree and we know the leading coefficient. Those are the things that really change what the graph looks like. Okay, so we look at this one and we see we got an x minus 1 squared and then an x plus 3. Is it? No. What's the degree? Degree is 3 because you got this one's going to turn into an x squared and then you're multiplying by something with an x. So it's cubic. Well, no, I'm not saying multiply it out. I'm saying recognize that without multiplying it out. If you need to multiply it out, you could. That's just a lot of extra work that I'm not after right now. We'll get there in a second. Okay, so it's cubic. So what do we know about the ends?
They go
opposite directions. Okay, and the way it works is if it's positive, the right side goes up, left side goes down. Think about positive slope on a line. Positive slope on a line goes up and to the right, right? Negative slopes can go down and to the right. So if there's a positive leading coefficient, we know the left side is going to go down, the right side is going to go up. So when we graph that, we can see that what's happening there. So I'm going to go to my graphing calculator. Y equals, I don't need that other one. I'm going to clear it out, and I'm just going to type in this one. X minus 1. This one's a little tougher to get something with as far as transformations go, because there's two different pieces. So transformation is really not something we can talk about too much with this one. X plus 3. So there's a nice cubic graph. What we see here is some changes in direction. We got the left side going down. That's what we expected to happen. Goes up here. What would that point right there be called? What kind of maximum? A local maximum. This point here would be a local minimum. Does it have an absolute minimum? Absolute maximum? No. We know all those things. You guys, that's great. Those are things that we're going to need to be able to recognize about polynomials and their graphs. Okay. Look at what else is happening with this graph. What else is happening with that graph? How do you say it? I see the 3 here. And there's the 1. What are those points, though? They're x-intercepts. That's key. Y'all hear what Vivian said? She said it moved to the left 1 or to the right 1 and left 3. But that's not as big a deal as the fact that these are what? X-intercepts. Those are important places, right? We found x-intercepts for quadratics. We found x-intercepts for linear pieces. We found x-intercepts for piecewise functions. All of those things are important. What's another important point on this graph? There's a y-intercept right there, right? Important pieces. Things we've talked about with all the other types of functions we've dealt with. Kind of start thinking about those now for these higher degree polynomials. Okay, so nice little graph. I'm gonna snapshot that. Put it in our notes. Remember it. If you want to sketch it, that's fine. See, it didn't distort that one. That one looks beautiful. Hey, now let's look at this problem. So without graphing it, we'll check it with graphs. But let's look at that first. Let's say describe the transformations of f of x equals x to the third power for g of x equals positive 2 x plus 1 cubed minus 4. So got to remember our transformation stuff here. Down 4, that's right. Down 4, left 1, and Thomas, what else did you say there? Vertical stretch. The +4 or +1 inside, that's our left 1. The -4 on the outside, that's our down 4. The 2 out in the front is a number bigger than 1. Well, I am doing math. This is math. Knowing those transformations is math. I'm not working anything out.
Yeah.
No, I'm not plugging any x values in and working them out. I'm just saying what transformations happen to the cubic function based on this. So this is a third degree polynomial with a leading coefficient that's what kind? Positive. So we know what's going to happen with our graph. It's going to left side down, right side up, right? And then we know it's going to take that regular cubic function and shift it down 4 and left 1. And then it's going to stretch it out a little bit based on that. Let's verify that with a graph. So look at that graph. 2 parentheses x plus 1 cubed minus 4. That looks like the x cubed graph. And normally it goes to the origin. So we can see it's down 4 and left 1. And, you know, we can put the other one up, the original up here. We see it's a little skinnier when it's stretched out. We put the other one right next to it. We would see that it's skinnier. Okay. So recognizing those pieces based on transformations. All right. Let's look at this one. F of x is equal to 5 parentheses x minus 2 parentheses x plus 3 squared parentheses 2x minus 3 cubed. We want to describe the zeros of the polynomial. It's a little terminology mixed in with this. All right. Well, it's a polynomial. So one of the things we wanted to talk about is the degree. What's the degree of this polynomial? 6y. Okay, got a third power, and that's going to get x cubed. Second power is going to get x squared, so x cubed, x squared is x to the fifth. And then x to the first, there's x to the sixth. So the degree of 6. Now, what that should tell us about the zeros, what's another word for zeros? Does anybody remember from our x-intercepts? That's the same thing. X-intercepts are zeros. That's what they are. So that means what we're doing is setting the entire polynomial equal to 0. That's what finding the zeros of a polynomial means. You're really finding the x-intercepts when you talk about the graph, but it's just zeros. And the good thing about this one is they gave it to us in what form? What form would we call that? Intercept form. We also called it factored form. It's already got factored. So that means what can I do with each factor? Set it equal to 0. What happens with the 5? It technically goes away. It really doesn't stay with anybody. You could divide by it and it's gone. So I'm setting x minus 2 equal to 0. So I really only have to set the things that have variables equal to 0. All right. I'm going to solve this first one. Plus 2. X is equal to 2. So that means we've got a 0 at x equals 2. That means the graph does what at x equals 2? It hits the x-axis. Touches the x-axis or goes, in this case, it goes through the x-axis at 2. All right? What about the second factor, that x plus 3 squared? What does that even mean? Yeah, it really means that it's 2x plus 3's. So that means I have two factors. Turns out they're the same, but it's important to recognize that, hey, I've got the same answer how many times? Twice. So it counts each time. Because the degree is 6 up here. The degree is 6. So that means how many answers should we have? 6. That matches every time. Now, some of them may be the same answer more than once. Like this case, we got x equals -3 with we call it a multiplicity of 2. Okay? X equals -3 with a multiplicity of 2 because it counts twice. Not a hard thing to recognize there. We're going to look at the graph of it in a little bit. I'm going to show you some interesting things that happen based on this multiplicity. Okay. Now we got this other factor, 2x minus 3 to the third power. So how many times is it going to count? 3. It has a multiplicity of 3. So we're just going to solve 2x minus 3 equals 0, and we'll get x equals 3 over 2 with a multiplicity of 3. And I just abbreviated multiplicity, and that's what I would expect you to do. MULT of 3. Okay, so we have zeros of 2, -3, and 3 over 2. But they count differently. This counts once, this counts twice, 2, 3, 4, 5, 6. Now we count 6 to get a total of 6 answers.
Does that mean the x is repeat?
Yes, it means the x-intercepts repeat. And it's based on the factor repeating. Is what's happening there.
So is it considered not a function?
No, it doesn't. It's still considered a function. The x values don't repeat when we plug them in because we got the other factors to take care of those. So they get a different, x values don't repeat with the graph of this. Let's look at the graph. I want to show you something that's happening with this. The degree is 6 because when you look at the original problem, this first part, the x minus 2, gets x to the first power. This one gets x squared, so that's 2 more. This one gets x to the third power. So there's a total of 6. That's how that's happening. The degree, what you got to think about for when it's written like this is if I multiplied it out, what would happen? What would be the highest exponent? So you just look at the first term in each factor and the exponent that's on it. And that'll help you. All right. So let's look at the graph and see what's happening at these x-intercepts. We know where they will happen. They will happen on the x-axis. So let's see what happens with that. So with your graphing calculator, let's go to y equals. And then we got a 5, parentheses, x minus 2, parentheses, x plus 3, squared, parentheses, 2x minus 3 to the third. Just type in that original polynomial. We see some weird stuff happening there. That's weird, isn't it? Do what now? Zoom 6 should be able to.
You can't see all of it in 6.
X plus 3 squares. Yeah, that's right function. I'm going to zoom out a little bit. Maybe my resolution is a little low. Yeah, there's that piece that you are seeing. My resolution was just a little too low to see that. Now, what we could see here, I'm going to zoom in on those spots where the x-intercepts are because that's what I want to talk about is what's happening at the x-axis. So I'm going to zoom in at, what was it, -3 was one of them. graph, zoom, 2. I'm gonna go over here somewhere close to -3. Whoops. Close to -3. And I'm gonna have to zoom in one more time. Yeah, resolution is still too low for a tab. Zoom. All right, I'm gonna zoom. That point, that right there, there's -3. So I'm gonna zoom in one more time there, and we really are gonna see what's gonna happen here. One more. That point in the middle is still -3. We see that line is getting down there close to it, right? I'll zoom in one more time. Maybe we'll see it here. All right, that's perfect. That's what I want to see. Gets down here to -3, and then what's it do? It comes down and then bounces off of it, goes up. The reason it does that is the multiplicity. What's the multiplicity for the x-intercept of -3? The multiplicity of 2. It's an even multiplicity. Even multiplicities bounce. Okay, that's one thing you need to. I write that down. Even multiplicities bounce. Even multiplicities bounce off the x-axis. You might. I think I call it bounce, but you could say touch. Now let's look at what's happening with that graph at one of those, at the x equals 2, wasn't it? Yeah, +2. So I'm gonna hit zoom 6, go back to my regular window, and then I'm gonna zoom in on the +2 because I know it does go all the way down to the 3 and hits it. Yeah. You gotta zoom in a lot. What that graph is doing is it's really, really skinny right there, and the resolution on these calculators is not retina screen iPad resolution at all, even on the newest. You gotta just keep zooming in, and it's there. You start seeing it now, and then you gotta zoom in again. Now you can see. So you move the window down a little bit more. It does go down and touch the 3, the -3 on the y-axis, on the x-axis. So we got this intercept that's happening here, and then we have right here at 2, or yeah, +2. We got something going in. So I'm gonna look at what's going on there. So I'm gonna zoom in over here close to where y is 2 and see what's happening. Does it look like it's bouncing off the x-axis there? No. It's going through it. What's the difference? Hit that button like 80,000 times. I have no idea. It's still moving. Yeah, it doesn't have a multiplicity. Multiplicity is technically 1. That's right, Ollie. That the multiplicity is technically 1, but it goes through the x-axis here at 2. What's it doing here? What x-intercept is this? The 3/2, right? What's it doing on the x-axis there? Does it bounce off? It's like it's going through it. Bouncing off would mean it doesn't cross it.
So it doesn't do both?
No, it can't do both. It either has to go through it or bounce off of it. Okay? Kind of like that wall. If you run at it, you either have to go through it or bounce off of it. That's kind of the way you want to think about it. And so here, what's the multiplicity on the 3 over 2? What's the multiplicity on the 2? 1. What kind of numbers are those? Odd, as compared to the multiplicity of 2 being even. So odd multiplicities are going to do what? Go through. That's another thing. Odd multiplicities cross the x-axis. That's the way I talk about that. They go through it, cross it, whatever you want to say. Okay. Now, that example is pretty on purpose so that you don't rely totally on your graphing calculator to do everything for you. You've got to know, because you couldn't see that x-intercept of the -3 because the resolution was too low on your calculator. Nothing you could do about that other than zoom in, but you'd have to know it was there to know where to zoom into. So that's where, technology is a great thing, but it fails us at some point. We've got to have some knowledge to go with it. So you've got to be able to do that. With these graphs and these polynomials, there's these things called turning points. Those turning points, you guys recognized them earlier when we were looking at these graphs up here. Like we were looking at this cubic graph here. Y'all said that point was a what? Like local maximum and local minimum. Those are your turning points. Okay? And finding those, we'll figure out how to do that. We'll talk about that later in the chapter. But knowing how many there should be is really easy. Okay, so turning points, polynomials of degree n have at most n minus 1 turning points. Okay, so whatever the degree of the polynomial is, subtract 1, and that's how many turning points it could have. Not necessarily that it does have those, because depending on what else is going on in the polynomial. But what I want you to be able to find is how many turning points would it have, or could it have? And we'll later on figure out. In calculus, there's really some neat ways to find those actual points. But the big deal here is how many turning points does it have? So let's look at an example of that. F of x equals x cubed plus 3x squared minus 5x plus 4. How many turning points does f of x have? What's the degree? Turning points, 3 minus 1 is 2. At most 2. It may only have 1, depending on the graph. We could look at the graph and see that. But instead, if that's the only thing we're asking for, why graph it? You should just look at the degree and subtract 1 from it. That tells you how many you could have. And that's one of the things that we want to know. All right. So the last thing is doing some algebra. And we're actually going to form some polynomials. Form a polynomial in standard form with zeros, 1, -2, and 3 with a degree of 3. Does it make sense that it should have a degree of 3? I got how many zeros? 3. Degree of 3. Now, so how do we build that polynomial? If the 0 was a 1, what was the factor that got us that? X minus 1. If the 0 was -2, what's the factor that got us that? x plus 2. And if 0 is 3, it was x minus 3. Now that's intercept form, factored form. We want to put it in standard form. How do we do that? Multiply them out. Pick 2, do those first. I'm going to do these 2 first. That should be x squared minus x minus 6. And then I'm going to multiply by x minus 1. Doesn't matter what order you do that in. I don't care. I just do it in that order because that's makes me feel comfortable doing these 2 together and then distributing the last one. There are some shortcuts sometimes. Like if you had like 2 factors, like an x plus 2 and an x minus 2, they weren't beside each other. Those are really quick to multiply together and get x squared minus 4. Difference of squares factors. Recognizing those can speed you up, but it's still the same process. So I'm going to distribute x cubed minus x squared minus 6x. And then I do this thing where I stack it up. When I multiply the next piece, negative 1 would be negative x squared, positive x, and positive 6. And that, I line up the like terms. I don't know if it helps or anything, but I don't know. I think it helps me keep from messing up. So there's my standard form for that cubic polynomial, 3rd degree polynomial. How can I verify that that's the right one? I could graph it, right? See where it crosses the x-axis. Where should it cross the x-axis? At those 3 points. Should it go through the x-axis at those 3 points or bounce off of it? Through, because it didn't say anything about multiplicities on those, right? Okay. Let's look at one that does. Again, most of this, it's kind of long. Zeros, negative 3, with a multiplicity of 2. And 5. So negative 3 has a multiplicity of 2 and 5. The degree could be 3. They're going to tell you those things. That's what you're going to get, that information, and you're supposed to build a polynomial in standard form from that. Okay. Now I'm boring and call mine f of x. You can call them g of x, z of x, k of x. I don't care what you call them. Name them whatever you want to. Okay. What are my factors? X plus 3 twice, so I'm just going to call it squared. And then the last one, x minus 5. The x plus 3 squared takes care of the negative 3 with a multiplicity of 2. If you want to write it twice, that's fine. I just write it with the square because I know what I'm going to do next. Okay? So multiplicity of 2, x plus 3 counts twice. If it was multiplicity of 3, what would the x going to here be? A 3. And if there's x multiplicity of 4, so on, you could do that. And then the 5 has one multiplicity of 1 because they don't say anything. So that's x minus 5. So then you would multiply that out. So that's x squared plus 6x plus 9 times x minus 5. So that's quicker to go ahead and multiply that out to me because I know how to do that. Algebra 1, we square binomials a lot. Algebra 2, you do that too. Because it's negative 3 here. So like when you set that factor equal to 0, that's how you get negative 3. So it's the opposite. Always change your sign. That's what you want to remember.
So why not do 3 in the second one if the first one's multiplicity of 2? Why is the next one?
Because x minus 5 is the other 0. So negative x minus 5 is the factor that gets you there. Yes, this is negative 3 with the multiplicity of 2, and 5 are the zeros with a degree of 3. All right, and then multiply that back out again. Get x cubed plus 6x squared plus 9x minus 5x squared minus 30x minus 45. Add it up. X cubed plus x squared minus 21x minus 45. Oops. Can't draw a box. And there's our standard form polynomial, the degree of 3. Out of that. Make sure they don't do any imaginaries. I'm pretty sure they don't. But no, they don't. All right. So that's section 5.1. Good bit of information introducing you to polynomials of higher degree. This is where when you were in Algebra 2, you did synthetic division, things like that. That's coming up. Remember doing synthetic division with polynomials. A lot of this chapter is a repeat of Algebra 2 stuff that you've done. So it should be familiar to you for most of us anyway. If it's not that difficult to learn if you can just kind of pick up on the pieces as we go. So it's that.